Hello, everyone. I hope you can hear me well. My name is Philip Boyd, and this is my final project for the Machine Learning Foundations for Project Managers course. Hopefully, in this presentation, I'll be able to walk you through the full modeling process that I used to predict the net hourly electrical energy output of a combined cycle power plant using machine learning. This has been a fun course, so I'm excited to showcase some of the skills that I learned. So the problem that we're solving here is a regression task. You're predicting a continuous variable, the net hourly electrical energy output, which was labeled PE, based on ambient environmental factors like temperature, pressure, humidity, and vacuum, lastly. So since this is a supervised learning problem with numeric output, I chose regression algorithms. I also selected a root mean squared error, aka RMSE, which you can see in the middle here. I wish I had a pointer with the chart that I created here on Canva as the main evaluation metric, since it penalizes larger errors and it gives insight into the model's prediction accuracy in megawatts. I also tracked the R-squared score to understand how well the model explains variances in the output. So the data set included 9,568 hourly observations, I believe, within the 5 columns. The columns were temperature, AT, V, which was exhaust vacuum, AP for ambient pressure, RH, which is relative humidity, and then, like I said, PE, which is net hourly electrical output, aka our target. So I used all 4 of the input features. For algorithms, I started with the baseline linear regression. Okay, you can see that on the top there. Model to capture simple relationships. Then I trained a random forest regressor to capture nonlinear patterns and feature interactions. Within this, I split the data set into 80% training and 20% testing. And during this training, I used default hyperparameters for both models for simplicity and reproducibility. Although I didn't implement full k-fold cross-validation due to running out of time, I'm very busy at the moment, I ensured fairness by using the same random seed and test split across both models. So as I said, I have the table up here, and here are the results. Linear regression had an RMSE of 4.50, I'll just round down there, and an R-squared of 0.93. Random forest performed better, of course, with an RMSE of 3.25 and an R-squared of 0.96. This means the random forest model is more accurate and captures more of the variability in power output, likely due to, as we learned, its ability to model nonlinear relationships. So, lastly, I just would like to talk about, an RMSE MSE of 3.25 means the random forest model predicts the plant's energy output within about plus or minus 3.25, as I said, megawatts on average. A strong result for energy forecasting. The R-squared of 0.96 means it explains about 96% of the variation in energy output, which makes it pretty reliable, I would say, for operational or planning purposes at a power plant. Not perfect, but definitely reliable. And then, as I've included here in the presentation, here's the model of the comparison results I generated using Python, scikit-learn, and pandas. So, still learning this, but this was really cool to add to my repertoire, and I really appreciate you guys for listening. I try to visualize and validate both models, and this helped me choose the most effective one. So to summarize, what you were looking for. I defined a regression task. I used all 4 sensor inputs as features. I trained and compared linear regression and random forest models. I chose the RMSE as the main evaluation metric, and I found random forest to be the better performer. If this were a real-world project, as I was doing research, next steps would include hyperparameter tuning, cross-validation, and model deployment. But thank you for listening. I hope I didn't go over the 5 minutes. If you have any questions or feedback, I'd love to hear it. Thank you again.